Okay, so now we are going to take a look at the second part of Newton's laws, and this is going to help us explore some additional phenomena with this. So we've talked a lot about friction, but we haven't really explored what it is yet, and we're going to incorporate quite a bit of that in this next section. So friction is what opposes sliding motion. So anything that's moving is going to have some sort of friction as it, and that friction is going to oppose its motion. And it has to do with the irregularities, even in smooth surfaces, that's holding it back. And friction is highly useful. We can walk, we can drive, we can sit in our chairs. We can do a lot of things that we otherwise couldn't do without friction. And it also dissipates energy, and we're going to look at that as we get into the energy section, but it takes away from energy in the system. So if we look at this block on ice, we can zoom in real far here, and we can see the if we zoom in, the irregularities in both of the block and the ice. And so as we try to push this, there's going to be some resistance to that. So even though the surfaces can look really, really smooth, there's going to be a resistive effect there. And so the direction of friction is always opposite of the movement. So we have the normal force, we have the force of gravity or the weight, and if we're pushing it to the right, the friction is going to be acting towards the left and opposing the push. Okay, so one of the factors that affects friction is how much normal force you have. And it's actually directly proportional. The friction is directly proportional to how much normal force there is. An increase in the normal force increases the amount of friction. Decrease in the normal force will decrease the amount of friction. And so an example would be if you took a shoe and you were pulling it, let's say like this way, there's friction back this way. As soon as you put more force on this, where the normal force increases, what will happen is it will take more to pull it because there's more friction. And so in class we had some examples with that. So static friction occurs between two surfaces that are not slipping relative to each other. So this is when an object is not moving yet, and you're pushing or pulling it, and the friction is opposing the movement. And it's an inequality. The force of friction, the force of static friction, is less than or equal to the coefficient of static friction times the normal force. And so the reason it's less than or equal to is because if you're pushing something, let's say pushing this object, you could be pushing on it before it even actually moves. You could try this with anything that's on your desk. If you're pushing on it and it's not moving yet, you could push a little bit more and maybe it still won't move. And so friction can be, the force of static friction can be less than the maximum. But once you overcome this number, once you overcome the static friction, it's actually going to start to move. The coefficient is unitless, and the normal force is in newtons, and the static friction will come out in newtons. So the greater this number is, the greater the coefficient, the greater the static friction will be. So the stickier or the more resistant it is to movement, the higher the coefficient will be. And the static friction between two surfaces is zero unless there is a force trying to make the surfaces slide. So just an object sitting there will not constitute actually any static friction until you actually try to push it or pull it. And static friction can increase as the force trying to push an object increases until it reaches the maximum allowed value. And so once you reach the maximum amount where you place the static friction times the normal force, whatever value that is. Let's say it's 33 newtons. You can push on something. Let's say you push on something with 31 newtons. It's not going to move. The 31 newtons this way, you're going to be opposed by static friction at negative 31 newtons. But as soon as you go over 33 newtons, the object's going to start to move. And that's the point at which the surfaces begin to slide. So once you exceed whatever the static friction is, it's going to start to move. So let's take a look at an example of this. You can draw a free body diagram of a fridge. So we've got the force of gravity here, we've got the normal force, and let's say we're pushing it this way, and with the force applied, what minimum force is required to get it moving? In other words, what is the maximum static friction force? And once we know that, we'll know that we've exceeded it, and yeah, it's going to start to move. So once we draw the free body diagram, you know, we can set up negative y, positive x, negative x, and establish our sum of the forces in the y equals ma in the y. So we have the positive normal force plus the negative force of gravity equals, now as this moves across the floor, and in this case we're even just getting it moving, the acceleration is 0 in the y direction, right? So it's not even moving in the y, so the velocity in the y starts and finishes at 0, the acceleration is 0. So in this case, the normal force is going to be equal to force of gravity, and that's going to be an important part of what we're going to do here. Now the force of static friction is less than or equal to the coefficient of static friction times the normal force. So once we find this, we can place this in here for the normal force, and we can figure out what the maximum force of static friction is, and once we overcome that, it's going to start to move. So why don't you go ahead and do that? Go ahead and calculate the normal force, then calculate the maximum static friction force, and once you do that, you can continue the video. So go ahead and pause and then give that a try. Okay, so we should get for the normal force 1,176 newtons, and the force applied, therefore, if, and again, this is you calculated this force of static friction here, the maximum coefficient, or the maximum static friction force would be 27.048. So if we, you know, exceeded this value, 27.049, let's say, it's going to start to move. Now, once an object starts moving, we have what's called kinetic friction. This is where the surfaces are slipping past each other. And this is an actual value that we're going to be able to get, the force of friction kinetic. And it is an equal sign because we're going to get that value in it, and it is that value. It's not an inequality like static friction is. So when we multiply the normal force times the coefficient of kinetic friction, we'll be able to determine the force of kinetic friction. And that's that value no matter how fast the object's moving. So we'll get that value and we'll be able to evaluate it. So again, the coefficient is unitless. And we can multiply that by the normal force here, and we can get the coefficient of kinetic friction. Oh, and this is also really important. The kinetic friction is generally less than static friction. It's easier, once something is moving, it's easier to keep it moving than initially to get it to move. And the example I like to use is moving furniture. It's really hard to get something, you know, large furniture item to move, but once you have it moving, it's a lot easier in terms of friction to oppose that friction. Okay, so let's go ahead and go back to the example that we had with the fridge that we got to move, you know, once we exceeded the static friction. And now what we're going to figure out is what is the minimum force required to keep the fridge moving with a constant velocity. So here's the coefficient of kinetic friction. and we're going to be able to use that to figure out what's the force required to keep it moving. So let's go ahead and draw a free body diagram. Force of gravity, normal force, force applied, force of friction acting and opposing the motion. And we'll just go ahead and set up our sum of the forces in the y equals ma in the y. Sum of the forces in the x equals ma in the x. Okay, so what I want you to try is go ahead and continue the sum of the forces in the y. Go ahead and determine the normal force. And then once you know the normal force, that will help you into what to do here with the sum of the forces in the x, where it's going at a constant velocity. So once you do that, see if you can figure out what the minimum force applied would be to keep it moving at constant velocity. So go ahead and pause the clip, and then when you're ready, you can hit play. Okay, so we have the positive force applied plus the negative force of friction. The key here is going at a constant velocity, so the acceleration is 0. The net force, positive force applied plus the negative force of friction equals 0 because acceleration is 0. Keeping it at a constant velocity. Remember, acceleration is the change in velocity over time. So if there's no change in velocity, the velocity stays constant, the acceleration is 0, the forces are balanced. An object in motion will stay in motion at constant velocity as long as there's zero net force. The normal force will equal the force of gravity. So we should get 1,176 newtons. And then for the force of friction, we have the normal force times the coefficient. And in this case, it's going to take 15.288 newtons to keep it moving at a constant velocity to oppose the friction. So friction is going to be 15.288, force applied is going to be 15.288. And as we pull it, in this case, or push it, it's going to stay at a constant velocity. And that's the common misconception, is that this number has to be greater. The force applied has to be greater than friction. But remember, if the net force is 0, an object in motion will stay in motion at a constant velocity. Newton's first law. The next question I want you to think about is if the fridge is pulled with an extra 20 newtons of force, what is the acceleration of the fridge? So why don't you go ahead and try that using the same values that you had, but in this case you will have a net force and an acceleration. So go ahead and pause the clip, see if you can figure out what the acceleration would be with an extra 20 newtons of force. Okay, so same normal force. In this case, force applied is going to be 20 newtons plus the 15.288 that we had before. And we should get an acceleration of 0.167. So this is how much faster it's going to be getting every second. Because we overcame the kinetic friction and we have even more force, and with that it will actually get faster. Okay, so let's go ahead and try one where we're looking at force at an angle, and we're wanting to determine what the acceleration of this object is. And so we have a 30 kilogram bag that's pulled at a 30 degrees above the horizontal with a force of 80 newtons. And we have the coefficient of kinetic friction. We want to find out what the acceleration is. So if we draw a free body diagram, we've got the force of gravity, normal force, and the pulling at 30 degrees above the horizontal, something like this, where we have, we'll break that down, force applied like that. This angle is 30 degrees, and we pull the bag at 80 newtons at the force applied there at 30 degrees. And so, and then we have friction acting backwards, force of friction. Okay, so let's go ahead and set up the sum of the forces in the y, equals ma in the y. Sum of the forces in the x equals ma in the x. And what you're going to do is, remember with the friction force, we have the friction force, we have to consider the normal force, and so we'll do that. But we have to determine the normal force. We're going to have to consider this force applied. So we have force applied on the x, force applied on the y, and the force applied on the y is acting upwards. The force applied on the x is horizontal there. So go ahead and use your trig to figure out what the force applied on the x is, what the force applied on the y is, and then see if you can set up the variables for the sum of the forces here, the sum of the forces here, and then yeah, go as far as you can, and you can pause the clip and see if you can determine the acceleration. Okay, so let's see how you did. We should get for our sum of the forces in the y, positive force applied in the y plus the positive normal force plus the negative force of gravity equals 0. And then for the x, positive force applied in the x plus the negative force of friction equals ma in the x. And to get the force applied in the y, we have 80 newtons, which is the hypotenuse times the sine of 30. And we've got the force of gravity, which is 30 kilograms times 9.8. And we bring that to the other side and then subtract. So we should get 254 newtons as the normal force, and the force applied in the x is the hypotenuse times cosine of 30 to get the adjacent side force applied in the x. Force of friction is the coefficient times the normal force, which you have here, the coefficient times the normal force. So we've got the mass 30 kilograms, and so when we add those up, we'll get a net force here. And we divide by 30, and we get the acceleration. So this bag is going to accelerate pretty rapidly, 2.03 meters per second squared at that force. Okay, so here's a picture of a bag that's being pulled at an angle, and we can evaluate that similar to what we did in the last problem there. So let's say that we have this bag that's being pulled at 33 newtons and 40 degrees above the horizontal. We have the mass, we have the coefficient of kinetic friction, and we want to find the acceleration. So go ahead and draw the free body diagram and break down the forces, set up the sum of the forces in the x, sum of the forces in the y, and try to work it all the way through. And you can pause the video, and then when you're ready to check your answer, you can hit play. Okay, so we've got the positive y, positive x, negative x. We can break down our force applied on the x, force applied on the y. Set up our sum of the forces. We should get positive force applied on the y plus the negative force of gravity plus the positive normal force for the force applied on the x. Plus the force of friction, that's the sum of the forces in the x, or the net force in the x equals ma in the x. For the normal force, we should get 125.79, and we're going to use that for our friction value, which is right here, the normal force times the coefficient. We have the force applied in the x, 33 times cosine of 40, and we should get an acceleration of 1.5 meters per second squared.